So we're going to look at some more definitions now. And we're going to look at the definitions of prime and composite. And these are going to be in terms of universal and existential statements. So we're going to say an integer n is prime if and only if it's bigger than 1, and for all positive integers r and s, if n equals r times s, then either r or s equals n. And we're going to say an integer n is composite if and only if n is at least 1 and n equals r times s for some integers r and s with 1 less than r less than n and 1 less than s less than n. So prime, the definition of prime, if we look at it, it basically says like if you can factor it into positive integers, a product of positive integers, the only way to factor it is 1 times n. But composite, there's another way to factor it other than 1 times n. And if you look here, this first one has a universal statement in it. The second one has an existential statement in it. Okay, so let's look at an example. Part A is 1 prime. So look up at your definition of prime. Take a minute and answer, do you think 1 is prime? So if you look at the definition, in order to be prime, n needs to be at least 1, bigger than 1. So there's no way that 1 could be prime. So no, we're going to say a prime number is required to be greater than 1. All right, part B, let's write the first 6 prime numbers. So the first prime number, right, is 2. You can only write it as 1 times 2. 3, not 4. 5, not 6. 7, not 8, because 8 is 2 times 4. 9 is 3 times 3. 10 is 2 times 5, so 11. Not 12. 12 is 2 times 6. And 13. So that's the first 6 prime numbers. Now let's write the first 6 composite numbers. So 2 and 3 are prime. The next one is 4. 4 is 2 times 2. 5 is prime. 6 is 2 times 3. 7 is prime. 8, 9, and 10. Those are all composite numbers. And so is 12. So here, if you're looking at, notice like every number bigger than 1, every integer bigger than 1 is either prime or composite. And that's true in general. Every integer that's at least 1 is either prime or composite.